Okay, so welcome back everybody to the session on precise orbit determination. Thank you all for waiting these 10 minutes on site and online. And we will move on with the next talk given by Sergei Rudenko from DGFI on precise orbit determination of SLR and altimetry satellites. So Sergei, the screen is yours.
Thank you very much. Hello everybody. So I would like to acknowledge my co-authors, names of whom are mentioned here. So as everybody of you already knows, a new realization of ITRF, namely ITRF2020, was released in April this year. And orbit analysts, along with other specialists, were invited to test and to validate, evaluate this new terrestrial reference frame realization. And we did that at the DGFI. First, for precise orbit determination of SLR and altimetry satellites using SLR observations. And in my presentation, I'm going to show you the results of this test for POD, but also additionally for altimetry crossover analysis, and to compare the results that we obtained for ITRF2020 with those that we obtained using SLR 2014. So as it was already mentioned in two previous presentations on new realizations of ITRF 2020, the main updates in them are 6-year longer time span of observations, use of data from new tracking stations and satellites, also improvement of station hardware due to technological advances in measurements methods used. In two reference frame realizations, it was an attempt to compensate nonlinear station motions using different approaches. That was periodic signals and processing deformation for ITRF, and non-tidal loading and post-seismic deformation for DTRF. Also, modeling of 4 geodetic techniques in reference frame realizations was improved. But what is completely new in this realizations as compared to previous one for SLR station is that long-term mean biases of SLR stations were derived for the period from 1993 to 2020.5, and they were subtracted from the time series of stations positions provided to ITRS combination centers. As we also heard this morning, these long-term mean biases were, however, not published yet. And so I'm going to show you the results of our test that were done for altimetry satellites, topics JSON 1, JSON 2, JSON 3, covering totally about 30-year time span, and that was done using SLR observations for 2 reference frame realizations that I mentioned already, and for ITRF 2020, we used complete modeling available for this reference frame. So we did that using a dynamical approach, using up-to-date models for precise orbit determination, and estimating also some dynamical and empirical parameters during orbit determination. It's very important to mention that to do that, we use the latest officially published version of ITRS data handling file, a version of 16th of June of 2020. And in this analysis, of course, no long-term mean biases of SLR stations were applied for ITRF 2020 since they have not published yet. And so the purpose of my presentation is to show importance of these biases and to show what differences in the orbit qualities and also altimetry crossover analysis occurs when these biases are not used. And to do that, for each TRF realization of our test, we computed 2 cases. when we estimated and not estimated SLR range biases for each station during precise orbit determination at 3.5-day orbit arc for each satellite. And in this and following slides, I'm showing you some results. So at the top slide, you will see the results for the case when no range biases are estimated. In this case, this is for RMS fits of SLR observations when we use two reference frame realization. And we observe here increase of RMS fits for ITRF 2020, especially for the period from 2007 to 2011 and from 2016 to 2021, compared to SLR 2014, when no range biases are estimated. The bottom figure shows you improvement reduction of RMS fits of both reference frames when we estimate range biases, and in this case, they are reduced by 25 to 33%, and even we observe that ITRF 2020 performs better than SLRF 2014 when we estimate these range biases at each orbital arc for each station. The similar pictures are for mean fits of RMS of SLR observations. So these are just arithmetic mean of fits at each orbital arc. And here we found that ITRF 2020 results in about 0.1 centimeter mean fits of SLR observations, while SLRF 2014 gives the value very close to 0 when no range biases are estimated. In case when range biases are estimated for both reference frame realizations, we obtain values that are very close to 0. So this slide shows the results for empirical accelerations, in particular for cosine of normal term. And again, we observe increase absolute mean and scatter of normal term of this empirical acceleration when we use ITRF 2020 when no range biases are estimated. When we estimate them, then the value of empirical acceleration decrease. Similar behavior can be observed also for another empirical acceleration coefficient. This is cosine of the long track term. Very interesting results were obtained for Earth albedo scale factor. In this case, ITRF 2020 gives notably smaller, shifted from one value of Earth albedo scale factor, namely 0.76. That is differs from the value that obtained using SLRF 2014, that is about 1.12. This is for the case when no range biases are estimated. So as you know, Earth albedo acts in the radial directions, so a scale of SLR solution change. So this is indication that SLR range biases have direct impact on SLR scale. When we estimate range biases at each orbital arc for each station, then we obtain closer to 1 realistic values of Earth albedo scale factor, and similar behavior is obtained for both reference frame realizations. This table shows you the average values of our test for reference frame realizations tested and parameters given here. So estimation of range biases for SLRF 2014 reduces RMS fits of observations, and ITRF 2020, as I said already, gives a little bit increased values of RMS fits, but using annual and semi-annual variations for ITRF 2020 allows to reduce RMS fits of observations. And as I said already, estimation of range biases for ITRF 2020 for both cases with periodical variations or without them even outperforms SLRF 2014 for the case when no range biases are estimated. So the two right columns indicate the results for atmospheric drag and solar radiation pressure coefficients. So we have not found significant impact onto these parameters, but it's logical because they affect or they estimate not in the radial direction. We compared orbits of satellites for the case of using two reference frame realizations, when range biases are estimated and when not. And we found increased RMS of radial orbit differences at the level about 4 millimeters for the case when no range biases are estimated, and they reduce to about 1.6 millimeters when they are estimated. And we found that ITRF 2020 orbits are shifted biased in the radial direction on average by about 1.3 millimeter with respect to SLRF 2014 when no range biases are estimated. Since we estimated range biases, of course, we have possibility to compare them. And here I show here an example for two SLR stations. At the top for Riga, using SLRF on the left and ITRF 2020 on the right. And we observed increased weighted mean and weighted RMS values of time series of range biases when we use ITRF 2020 as compared to SLRF 2014. And the figures at the bottom shows the results for another SLR station, namely Katsaveli, with similar increase of absolute values of mean and weighted RMS of range biases. This slide shows you the weighted mean values of SLR range biases estimated for one satellite, namely for JSON-2, during the complete mission duration using two reference frame realizations. And we found the stations listed here that provide larger absolute weighted mean of SLR range biases with ITRF 2020 compared to SLRF 2014. And we are pretty sure that these are exactly the stations for which larger absolute values of long-term mean range biases were computed and used for ITRF 2020 realization as compared to other SLR stations. And similar plot is here showing weighted RMS of SLR range biases. And again, the list is about the same. Some additional couple of stations are included. As I mentioned, we performed also independent altimetry crossover analysis. Here I'm showing the results for one satellite for JSON-2. So at the top left, you can see that standard deviation of crossover differences with ITRF 2014 is better than with ITRF 2020 when no range biases are estimated. When we estimate them for ITRF 2020, this is at the bottom left, we can see also improvement, reduction of this standard deviation of crossover differences. And when we estimate range biases in orbit, in both orbit solutions, then we observe almost no differences. And this is also can be quite good visible in this plot at the bottom right, then you can see here. We also look at geographically correlated mean error differences. This is important parameter also for orbit of altimetry satellites. And when we do not estimate any range biases, we observe south-north behavior of these differences. This is at the top left subplot. And on the right side, you can observe that these differences are somehow reduced when we estimate range biases for both reference frame realizations, and you can see almost no differences at the bottom left when we compute the differences for the cases when both range biases are estimated for both reference frame realizations. We also looked at the single satellite altimetry crossover differences and geographically correlated mean errors and radial errors. Here the results are for JSON2. And for all these three parameters, we observed some kind of degradation in case for ITRF2020 when no range biases are estimated, and better performance when they are estimated. So this brings me to conclusions and recommendation. Without the application of the long-term mean biases of SLR stations that were used to derive ITRF2020, this reference frame realization provides degraded orbit quality and altimetry crossover analysis results as compared to SLR 2014 for the case when no SLR range biases are estimated during orbit determination. So this shows importance of these long-term mean range biases. You can see the effect that they bring. And so publication of them is highly desirable and so at earliest convenience. And I would like to mention that these biases are also necessary to be used with two other reference frame realizations, DTRF 2020 and GTRF. And so in fact, proper evaluation of these reference frame realizations for SLR stations and also their use for validation of other space geodetic techniques can start only after the publication of these biases. And as long we don't have these range biases, so the proper way to use new ITRS 2020 realization is to estimate range biases of each station at each arc. So thank you very much for your attention.
Thank you, Sergei. Are there any questions on site or online to Sergei? Any comments? So, Toshi?
Sergei, very good talk. Thank you very much. I'm interested in your results of having 0.7 something for the albedo coefficients, which sounds not realistic. So I'm wondering, what is the real cause? I mean, is that maybe the ITRS2014 is the close to the reality, or perhaps GM or something different? Can you give us any thoughts?
Yeah, so thank you for your question. So our opinion that the real cause of this value of this, as you mentioned, not realistic value, is that we could not bring in our computation this long-term range biases. So some important information is missing to be used with ITRF 2020 for precise orbit determination. And this has resulted in this, as you mentioned, not realistic value of Earth albedo. If we would have long-term range biases, then it would result, as I show here, when we estimate, for example, them to realistic values of scaling factors for Earth albedo close to 0.6 or 1.8.
So in the matter of time, we move on to the next presentation, which is